Welcome back. We had mentioned earlier that while approximating, there sometimes we run into problems. In this lecture, we will learn how to handle those problems. Consider a flow between two parallel plates, long, infinite parallel plates. The upper plate is stationary, and the lower plate, a distance b below the stationary plate, is oscillating with the velocity that is given as v naught sine omega t. In such a flow, the forces of interest are the unsteady inertial forces and the viscous forces. Let's estimate those forces. The unsteady forces are estimated as mass times acceleration, and the mass is rho L cubed characteristics times the acceleration v by t, and so this gives rho Lc cubed Vc by Tc, where Tc is a characteristic time, Vc is a characteristic velocity, and Lc is a characteristic length. Similarly, the viscous forces are estimated as mu times the area times the velocity gradient, and that, as before, results in mu times Lc times Vc. The natural or the characteristic values of the various quantities in these estimates can be taken as Lc is equal to b, the spacing between the plates, Vc, the characteristic velocity, as v naught, the amplitude of the velocity of the oscillating plate, and a reasonable characteristic time is 1 over omega, the circular frequency. With these, the unsteady forces become rho b cubed v naught omega, and the estimate of the viscous forces is mu b v naught. Thus, the ratio of the unsteady to viscous forces is given by rho b square omega divided by mu. Now, at equilibrium, the unsteady forces must balance the viscous forces. The ratio rho b square omega by mu then determines the relative importance of two types of forces. If this value is small, that is, if omega is much less than mu divided by rho b square, the unsteady effects are small and may be neglected in comparison with the viscous forces. Once the unsteady effects are neglected, the governing equation would require that the net viscous forces be zero on any element of the fluid. Now, what's going on? I think there's something funny. We claim that unsteady force term must be equal to the viscous force terms. When we converted this into normalized variable, we get rho b square omega by mu times dv star by del t star is equal to del square v star by del y star square. The left hand side represents the normalized acceleration, and this is the normalized second gradient of velocity that occurs in the viscous forces. If the unsteady force term is small, we set viscous term is equal to 0. And if viscous term is small, we set unsteady term as 0. What's going on? It seems funny. If the unsteady term is small, we claim that if this is small, then the unsteady term is small, and we set the viscous forces to be small. Now, isn't this rather strange? If unsteady force is small, we should set unsteady forces to be 0 and not viscous forces to be 0. So, what is going on? Let's look at this equation that we derived once again. Note that even when rho b square omega by mu is small, the left hand side is not smaller than RHS. The two sides are always equal. This whole is equal to this whole. We expect this to be order 1. We expect this to be order 1. And if this is small, so hasn't something gone wrong? Yes, something has gone wrong. When rho b square omega by mu is small, it only means that at least one of the two derivatives which we were expected to be normalized are not normalized. At least one of the two derivatives is not of order 1. So, either del v star by del t star is much greater than 1, or del square v star by del v star square is much less than 1. So, if this is order 1, then this should be of order epsilon, where epsilon is this parameter, rho b square omega by mu. And if this is of order 1, then this should be of order 1 over epsilon. So, we expect when a situation like this arises, that is, when we have two terms in an equation that are equal, and after normalization, one of the terms has a coefficient which is very small, then the only way out is that we should suspect that our normalization is not proper. So we said that either del v star by del t star is much greater than 1, or del square v star by del y star square is much less than 1. Can del v star by del t star be much greater than 1? Recall that t has been normalized by Tc, the characteristic time, which is 1 over omega. Del v star by del t star would be much greater than 1 if the actual Tc is much smaller than 1 over omega. Is this possible? This would be possible only if the variation of v star with t star normalized by Tc is equal to 1 over omega is something like this. That it doesn't take the whole range of T star for V star to change from 0 to 1, but it changes from 0 to 1 in a much smaller interval. So, the time it takes to rise from 0 to 1 is not like Tc, but is much less than Tc, that is much less than 1 over omega. Is it possible? Can the fluid velocity inside, or can the fluid velocity between the two plates oscillate faster than the fluid velocity at the bottom plate, which is forcing the flow? That does not appear to be physically possible. It's not physically reasonable. Can del star V star by del Y star square be much less than 1? The other possibility. Sure, if del V star by del Y star is constant, the second derivative is 0. That is, if the variation of V star by T star is linear, clearly del V star by del star is constant, and del square V star by del Y star square is 0. It doesn't need to be a straight line. even if the variation v star by t star is given by a curve like the blue curve here, the second derivative del square v star by del y star square would be much less than 1. And so, there is a definite possibility that del square v star by del y star is much less than 1. If rho b square omega by mu is much less than 1, that is, if omega is less than mu divided by rho b square, the unsteady terms can then be dropped and we can set del square v star by del y star square is equal to 0. It is very small and we neglect it. So, this is a valid approximation. This directly or through the momentum equation gives del square Vx by del y square is equal to 0. That is, there is no net viscous force acting on the fluid. This is to be solved with the boundary condition, the no slip boundary condition at the lower plate, Vx is equal to V naught sine omega t, and the velocity is 0 at the upper plate. Again, a no slip condition. So, for omega less than mu divided by rho b square, or in terms of kinematic velocity, omega less than du by b square, kinematic viscosity divided by the distance between the plates squared, we get a solution like this. This equation with this boundary condition will give you what appears to be a quasi-steady solution. Depending upon the boundary condition, for any given time t, we calculate the velocity at the lower plate. And if this is the velocity at the lower plate, then the velocity through the fluid varies between 0 and this point linearly, like an aqueous flow. But this boundary condition is changing with time. And so, the velocity profile is oscillating. At any given instant, the velocity profile is exactly what is obtained in a steady flow. But as time changes, the boundary condition at the lower plate changes with time. And so, the linear profile between the lower plate and the upper plate changes with time. This is what is termed as a quasi-steady flow. Again, for omega less than nu by b square, we can interpret b square by nu as a penetration time tau. Notice that the dimensions of b square by nu are those of time. So, we consider the penetration time tau, the time it requires for the change of velocity at the lower plate to penetrate up to the upper plate. That is, time required for the velocity fluctuation at the lower plate to penetrate right up to the upper plate. Then this condition, omega less than nu by b square, translates into omega is much less than 1 over tau. That means the time required for flow velocity to penetrate up to the upper plate is much less than the time of fluctuation of the velocity of the lower plate. The lower plate is fluctuating far too slowly, such that at any given time the velocity appears to penetrate up to the upper plate almost instantaneously. And so we have a quasi-steady flow. In other words, if the time period 1 over omega of the oscillation of the lower plate is much more than this characteristic time, the motion of the plate is so slow that the unsteady inertia of the fluid can be neglected. We can interpret this alternately also. We can consider under root nu by omega, which is a dimension of length, to be the penetration depth Lp. That is, in the time of one cycle of the upper plate, how far does the effect of the lower plate motion penetrates upwards? The penetration depth. Within one cycle, how far does the effect penetrate? And if this penetration depth is much larger than B, then the effect penetrates through the distance B almost instantaneously. Same thing as before, except here we interpreted in terms of penetration depth, and earlier we interpreted in terms of penetration time. Penetration time is the time it takes for the effect to penetrate through distance B. And the penetration depth is the distance the effect penetrates in time 1 over omega. For both these considerations, we see that the motion of the plate is too slow. Therefore, for B less than under root nu by omega, we can imagine that the effect of the motion of the plate penetrates throughout the thickness of the fluid layer before the motion of the lower plate changes direction, or that the oscillation appears too slow to the fluid and it can be assumed to respond instantaneously. This was the easy part. Let's look at the other part. When omega is not less than mu divided by rho b square, but the opposite, omega is greater than mu divided by rho b square. And we'll soon see that it leads to a very serious complication. The principle of small causes producing small effects suggests that now we can neglect viscous forces. This leads to a very strange result. If we neglect the viscous forces, that is the right-hand side of our equation, the governing equation then becomes dvx by dt is equal to 0. This is a first order equation, so it admits to only one boundary condition. But we have two boundary conditions. The velocity Vx is 0 at y is equal to b, and the velocity Vx is V naught sine omega t at y is equal to 0. It cannot admit both the conditions. So this cannot satisfy our boundary conditions. So it doesn't appear to be a valid solution. This is an ordinary differential equation simply stating that the velocity within the fluid does not change with time. It cannot now accommodate the lower boundary condition. So there is something that has gone wrong in a formulation. And what could go wrong? The only thing that could go wrong is that the quantities that we have taken to be the characteristic quantities may not be appropriate. The resolution of this problem lies in recognizing that the distance LP through which the disturbances penetrate in time 1 over omega is very small compared to B. This is the same approach that Prandtl took to explain the formation of boundary layer on a flat plate. The oscillating plate produces a viscous effect. Because of that viscous effect, the velocity starts penetrating upwards. But before it can go through a significant distance, the motion of the lower plate changes direction. And so the effect over a long time is now restricted to a thin layer about the lower plate. The velocity changes from V naught sine omega t to 0 over this small distance rather than over the whole distance B. This means that the velocity gradient normalized by V naught divided by B is in error. When you obtain del Vx by del y and normalize it, then normalizing the distance y by b is in error. Only if it is normalized by V naught divided by LP, with LP is equal to under root nu by omega. Nu is the kinematic viscosity, mu by rho. Should the velocity V star be of order 1. So that the characteristic distance, the characteristic length in the y direction should not be taken as B, but as LP, the penetration depth, which is related to the circular frequency omega of the oscillation of the lower plate. So how is the problem handled? We divide the flow field in two regions. One, a thin layer of thickness LP is equal to under root nu over omega near the lower plate, and then the rest of the region. We term this region as the boundary layer. And we term this region as the outer layer. Boundary layer is very thin region near the oscillating plate. Viscous stresses can then be neglected in the outer region, in the outer layer, but not within the boundary layer, where neither the viscous nor unsteady effects can be neglected. So that we now obtain two equations, one valid for the boundary layer and the other for the outer region. And the flow solution would be this. The region for the outer flow is simply dvx by dt is equal to 0, as we have obtained in the last slide. And the upper boundary condition is applicable to this. And so the velocity is invariant through the outer region with time as well as with y, and we get Vx is equal to constant is equal to 0 throughout this region. But within the boundary layer, both the terms must be present. The unsteady force term as well as the viscous force term. Let's now talk about the boundary layer and derive the equation for that. The unsteady forces are estimated as mass times acceleration, and the mass within this region of thickness delta would be scaled like rho L square delta. L square in x and z direction and delta in the y direction. So mass is rho times the volume, and the volume would be like L square delta. And the acceleration would be like v divided by t characteristic, and t characteristic is like 1 over omega and v characteristic like v naught. So that this gives you v L square delta omega v naught. The viscous forces are estimated as mu times the area on which the viscous forces act times the velocity gradient. Now viscous forces act on an area which is like L square, and now the velocity gradient is v naught divided by delta rather than v naught divided by b. And this gives us the viscous forces as mu L square v naught by delta. Delta is as yet unknown. Now we assert that within this boundary layer, both the unsteady forces and viscous forces should be of the same magnitude. So this force should be about the same order as this. So we can set rho omega delta square by mu is equal to omega del square. So the ratio of the inertial to viscous forces is the inertial force divided by the viscous force is rho omega del square by mu, which in terms of nu, the kinematic viscosity, is omega del square by nu. And as I said, these two forces must be of the same order. So this should be of order 1. And that gives us delta. And this gives us delta should be order of under root nu by omega. The same result that we got earlier. This graph represents the results of the experiments done on 3 different fluids: water, motor oil SE 1540, and glycerine. Glycerine has the largest kinematic viscosity. And we see that for each fluid, delta varies with frequency. As the frequency increases, that is, the value of omega increases, the boundary layer thickness decreases. This is in line with this result. Let's do a similar problem. But in heat conduction, we have a slab of thickness B, one end of which is maintained as Ti, the initial temperature of the slab, and the other end is subjected to a fluctuating temperature. T is equal to Ti plus T naught sine omega t. The amplitude to naught and the circular frequency omega. The applicable equation, this is the energy, rate of storage of energy within this, and this is the rate of conduction of energy. They're equal with to be solved with the boundary condition T is equal to Ti for all x's for time t less than or equal to 0, and T at x is equal to 0, that is this end, is T naught sine omega t for t greater than 0. And then the temperature of this is always maintained at temperature Ti. Let's normalize this equation, and as we have done in other thermal problems, it is not the temperature but the temperature difference that matters. So we use a variable theta is equal to T minus Ti and normalize it with the amplitude of the temperature fluctuation T naught. We normalize x by B and time with 1 over omega. And when we do this, these changes, this is the equation that results. Normalized equation. With theta star is 0 for all x star and for t less than or equal to 0, and theta star is equal to x star is equal to 0. And theta star at x star is equal to 0 is sine t star for t star greater than 0. Here again, if we expect these to be normalized, then this parameter measures the relative importance of the conduction term and the heat storage term. This coefficient in terms of the thermal diffusivity alpha, which is K by rho C, becomes alpha divided by B square omega. So this is the parameter that determines the relative importance of the two terms. Same equation and boundary condition repeated. Now, for this parameter to be much less than 1, as before, we get delta theta star by delta t star is equal to 0. And since this is a first order equation, it can accommodate only one boundary condition. And so we run into a problem. It cannot accommodate the boundary condition at x is equal to 0. So similar to what we did before, there has to be an inner region, a boundary layer region, where the temperature fluctuates. So this area here is the area in which the temperature fluctuates. Near the left boundary, the characteristic length over which the temperature change takes place is like Lp, a penetration distance. So near the left boundary, the characteristic length over which the temperature change takes place is like Lp. So that if we define a normalized variable y tilde is equal to y over Lp, we have chosen a different nomenclature y tilde, not y star, because y star you may get confused by the variable when the characteristic length is b. So the resulting equation is delta theta star divided by delta t star is equal to alpha LP square omega rather than alpha B square omega. Now, as before, within this penetration region, within this boundary layer, within this inner region, the two terms should be of the same order. And if the two terms should be of the same order, then alpha L square by omega should be of order 1, so that the thickness of this layer is like under root alpha divided by omega. And we can write delta theta star by delta t star is equal to del square theta star by del y tilde square. And the temperature profile through this slab would be something like this. Of course, this is at a given instant of time. At another instant in time, this could change, but the change would be largely restricted to this region LP, and the temperature in the outer region would be constant at Ti. Thank you.